We will use PhET, the DC circuit lab, to investigate how Kirchoff's junction rule and Kirchoff's loop rule apply to circuits with components in series and parallel. So we'll begin by building a circuit. We're going to use one with multiple batteries and resistors. If we close the switch, we see that electrons begin flowing through the circuit. We're going to use a voltmeter. We note that we'll keep the voltage of the batteries at 9 volts, which is the default value, and the value of the resistors at 10 ohms, which is the default value. So to begin measuring the potential changes around the circuit, we get the black terminal of the voltmeter and we put it on the negative terminal of the battery and the red terminal on the positive terminal of the battery, and we can see we have a potential change of 9 volts over the first battery and 18 volts over the two batteries together. The second battery has a potential increase of 9 volts. If we check the change across the wire, we see that it's 0. The change over the resistor is minus 9 volts, so that's because energy is lost as current flows across the resistor. Across the ideal ammeter, there's no voltage change. Across this next resistor, we see the potential changes by minus 9 volts as well. And then over the final ideal ammeter, the potential change is 0. So if we add up the potential increases of the batteries, 9 volts plus 9 volts, that equals the potential drop across the two resistors. If we close the switch in the second branch of the circuit, and we can repeat this procedure, keeping the negative terminal always trailing behind the positive terminal of the voltmeter. So across the batteries, we increase in potential by 18 volts altogether. Then as we go around the circuit, the first resistor has a potential drop of minus 10.8. There's none across this wire. Then the potential decreases by 3.6. And then across this final resistor, it decreases by 3.6 again. So what this means is that all up, we've had an increase in potential across the batteries of 18 volts and a negative change in potential as current moves through the resistors of minus 3.6 over these two, which adds up to minus 7.2 altogether on the left-hand side. And if we include this resistor we went through first, which had 10.2 volts drop across it, then altogether we have a drop of minus 18 across all our resistors. So the increase in potential across the batteries equals the decrease in potential across the resistors around a complete loop of the circuit. We can also apply Kirchoff's junction rule to this circuit. If we look at the current flowing through the batteries, we see it's 1.08 amps. Here at this junction, the current splits and some goes through this branch of this parallel section of the circuit and is 0.72 amps. Some goes through this branch and this is 0.36. You see that these two together have to equal our 1.08 amps. So we're using Kirchoff's loop rule that the current into this junction equals the current flowing out. At this junction down here, we can see that these two add up together to give the current flowing out of the junction here, and that this again has to add up to 1.08 amps. If we open the switch, we see that now there's no additional branch and the current flowing through this series circuit is the same everywhere, 0.9 amps.